I know I'm the last person between you and coffee, which is very important. Real quick on it, my name is Vivek Kumar. I told my postdoc Peter when, let me do this one, right? So I'm going to talk to you a little bit about dental pulp regeneration using some of our novel self-assembling peptides. And if none of that makes sense, hopefully it will in a couple of minutes. So some of these technologies have been commercialized or in the process of being commercialized by a startup that I have called Nanjotex, and some others. Technologies have IP disclosures on them. Kind of got to throw this out there. Perfect lighting. Good. All right, so this is my lab, and I was telling Jane a minute ago that it's a little crazy, and these guys, quite honestly, hate me. Both Peter and Biplov, who manage all of these students. But today, it's not about me, it's about Peter, some of his work, as well as Saloni Patel and William Gao in dental tissue engineering, or dental tissue regeneration. Oops, that doesn't work. Okay. So, a little bit of background on what the problem is. So if anyone's had a root canal before, 15 million other people do that as well every year. What they do is they go in, they extirpate, yank out the soft tissue inside the tooth. They throw in some rubber rods, and essentially you have a pretty dead tooth, right? It's not sensory, you don't have structural or functional integrity, so it's there. And these procedures cost anywhere between $400 to about $5,000 per tooth per procedure. More often than not, a couple of years down the road, you need repeat procedures. You have a relatively dead tooth. Rubber rods don't really regenerate that well. The total market for this is about $6 billion per year. So again, some of the pathology, right? You have a caries infection, you have inflammation, cause a lot of pain. Take off an enamel, go in there, extirpate, remove the pulp. As you can see here, they got a whole bunch of different files. Love files. And what they do is they essentially remove all the soft tissue and they implant those rubber rods that I told you about right here, which are made out of, gotta purchase what they're called, they're made out of rubber. So what we want to do is introduce a new paradigm in the treatment and regeneration of dental pulp. What we say is, instead of going in there and extirpating all of the pulp, and even if you do, instead of putting in rubber rods, why don't we put in a bioactive material instead of a bioinert material? Why don't we try putting in a hydrogel, which is thixotropic, shear thinning, shear recovering, forms a gel in situ, into the pulpal cavity and regenerate tissue. And there were two considerations that we took into consideration when we thought about this. First of all, enhancing blood supply so that you have functional tissue that actually responds to infection and is not prone to reinfection, as well as dentin regeneration. And that's to do with mineralization as well as ensuring you have good structure of teeth. So, that worked. Okay. So I'm going to tell you a very quick story on what self-assembling peptides are. I'm no chemist, and hopefully you'll be a little more informed about what we do here. So our self-assembling peptides come off of this relatively simple sequence that was developed by Jeffrey Hartbrink over at Rice University. They consist of terminal, so just looking right here and right here, terminal, polar, charged amino acid residues. So these are lysines in this case, you can add glutamic acids and what have you. The mid block of these peptides are serine leucine repeats, so there are about 16 amino acids. Lysine, serine leucine 6 times, and then lysine. What we can do is introduce biological functionality into these peptides in terms of an LRG, it's obvious, right, what amino acid that is, an LRG MMP2 cleavage sequence, as well as an RGD sequence, enhanced cell adhesion, for example. And what we see, this was back at Rice, we have some good animators over there. These self-assembling peptides in aqueous solution form a hydrophilic phase and a hydrophobic phase, and as I mentioned, have these bioactive domains. So in aqueous solution, those hydrophobic regions come together, try to exclude that water out of there. Those red little dots are oxygen molecules and nitrogen molecules. And essentially, you have fiber self-assembly, as you see here, in the cross-perpendicular axis. I'm going to kind of wipe this right here. But basically, you've got lysine residues on the terminal of that peptide, ignoring the bioactive domains, right? And because you have those lysine residues, you have what we term, or what we like to think of as molecular frustration. When that next amino acid comes on, it's got that net charge, it gets repelled away. In formulation, shield those charges in some PBS, right? And if you have long-range fiber self-assembly, which essentially allows intrapeptide, intra-fiber cross-linking, ionic cross-linking. So it forms a nanofibrous matrix that looks like this. It's a 1 micron scale bar. We publish all this data. What's exciting about this is that, as I mentioned, they're thixotropic. Because they're held together by non-covalent interactions. All that chemistry just to tell you non-covalent interactions, right? Those bonds break easy, reform easy. Syringe aspirate, inject, the higher the shear, 30 gauge needle, the better it flows. It self-assembles in situ where you inject it and biodegrades over time. What we see is that this whole region here, to the left of that yellow line, is implant that we put in the subcutaneous space. And what's interesting, these red cells here, I'm not going to go into too much detail, are primarily CD68 positive macrophages. So we've come up with a variety of different things we can do from these scaffolds, including drug release, inflammation modulation, drug delivery, therapy angiogenesis, and essentially extending from that, crazy slide, extending from that, we've got thixotropic hydrogels, as I mentioned, inflammation modulation, we can enhance cell adhesion. And then what we said was, well, what if we took this RGD sequence and switched it out for a bone morphogenic mimic, right? Not the whole growth factor, a short mimic that you present in high epitope density. A bone morphogenic mimic, or a neurogenic factor mimic. And we have multiple students working on all these different things, or an angiogenic mimic, right? And essentially, there was this mimic published about just over a decade ago by a group in Italy, the D'Andrea group, where they published a sequence called QK, this little guy, stable hand, right here, which essentially potentiates angiogenesis. It's a mimic of VEGF-165, it self-assembles. You have extremely high epitope density. Instead of just putting growth factor in that diffuses away, it's self-assembled, it stays in situ. And what's really exciting, and this was pretty much the cornerstone of a lot of the work that we do nowadays, in the lab at least, is that this entire area here is hydrogel. Within 7 days, we're forming blood vessels, it's 100 micron scale bar, we're forming blood vessels several hundred microns into these implants, which are lined by green smooth CD31 positive endothelial cells, red alpha SMA positive smooth muscle cells. So we're forming venules and arterioles de novo, we like to think, in vivo, in the subcutaneous space. And as you can see here in this, I guess, oblique longitudinal section of the vessel, what we think is happening is that there's an on-off of these peptides, which creates that chemotactic gradient to the existing blood vessel, angiogenesis in, beautiful vasculature. Filed IP on that, started up a company called Nangiotex, and essentially we did a high-limit ischemia model. This was in association with Texas Heart Institute a couple of years ago, while I was doing my postdoc. And essentially what we saw was when we ligated the femoral artery, injected the peptide into the gastroc as well as the quadricep, calf, and thigh muscle. Within 7 days, rapid restoration of perfusion, and by 28 days, we see that these mice are running just as far as they did before surgery, right? And in fact, a little bit further. And when I pitched this to investor events and things like that, they're like, oh, super mice. Super mice. Good. We're on the same page. So what we did was we went to the FDA and we said, what is this? Can we weasel this in as a device? There's a PMA for Chugangsang's RADA peptide. They're using it for dermal applications out of MIT. Pure matrix, right? You guys know that. And so what we said was, can we use this as a predicate and try to get this into the clinic a little quicker? And they said no, because of two reasons. First of all, while it's a scaffold, it activates cellular receptors. It activates VEGF receptor 1, VEGF receptor 2, neuropilin 1, and because of that, you're a drug. And because you're made by solid-phase peptide synthesis as opposed to biological expression or what have you, you're not a biologic, so you're a drug. I said, what about combination products with devices elite? They said, you're a drug. So instead of putting an angiogenic mimic on, we decided, let's put a dentinogenic mimic on. And the mimic, and the mimic that we wanted to work with was called dentonin, right? So just taking a step back again. So the idea here is instead of taking a huge growth factor, covalently cross-linking it, where you wouldn't have as good presentation and not as good self-assembly because you have this huge bulky group that's preventing the self-assembly of those beta sheets, we said, why don't we take a mimic from a matrix extracellular phosphoglycoprotein. Just saying that, I remember the work that Jane does. I'm just waiting for the questions. And so MEEP is a sibling family of proteins, small integrin binding ligand, N-linked glycoprotein, found in bone and dental tissues. It helps with dentinogenesis. There was some literature published on how these help with dental pulp stem cells, the guys in the tube that help regenerate, right? Help activation and proliferation of DPSCs. That same platform backbone, and it self-assembles. Now clearly, I don't have the sequence on here for good reason, IP. And what we see is this stuff was sent into a beautiful nanofiber scaffold. This is SEM, that's 1 micron scale bar. So you can see that it forms a beautiful scaffold that we can syringe aspirate, again, syringe aspirate and inject. The finer the needle, higher the shear rate, better it flows. 30 gauge needle, right? So for those of you who are thinking about that. So we showed that it forms hydrogels, as you can see right here. We've done some chemical characterization. It forms antiparallel beta sheets with IR. And then we did some very simple rheology, right? And the idea here is that we do a frequency suite, so oscillatory rheometry. We do a frequency suite where we get storage moduli, how solid this is, loss moduli, how liquid this is. And what happens is, as we increase the angular frequency, or as we increase the strain rate, the amount it strains or how quickly it strains, they start to liquefy. We see a switch between the G double prime and the G prime. It becomes more liquidy and solid. G, that's the word, because liquidy was. And we see liquefaction of these hydrogels. So then the question is, do they get back some of that storage modulus? So what we did was a shear recovery test. We tested it at low strain rates, 1%, for about 30 minutes. We had a relatively stable G prime. And then we increased the strain rate to about 100%, and we know that it liquefies at 100% strain rate at very high angular frequencies, and we see that the gel liquefies, that G prime plummets for 1 minute. We relieve that, and within 90 seconds, we see that we recover close to 90 to 95% of that G prime. You inject it, and it rapidly reself-assembles. So, let's see here. Did not switch. Try again. All right, so we did a little bit of AFM to characterize the fibrillar structure and the dimensions of these peptides. And what we see in the high profile, because it's nice and small there, in the high profile, excuse me, these peptides, these nanofibrillar peptides are about 2 microns tall. So if you look at the molecular size of the cell assembly, it should correspond to 2 nanometers. I did say 2 nanometers. You heard me wrong. And in terms of the width profile, how wide these little ribbons are, they're about 30 nanometers. And when you actually measure what those amino acids line up to, it's about 30 nanometers. That's essentially quantified in this little graph here. And what we did was very simple cytocompatibility. We got to put a couple more fibroblasts on that plate and then see whether they proliferate with low concentrations of this peptide. In addition to that, I don't have the data with me, but we've loaded these cells, loaded a variety of different types of cells, both fibroblasts as well as desert pulp stem cells, into these hydrogels in 2D and 3D cultures. These hydrogels support very good 3-dimensional culture of cells. And, where's Alex? Dr. Lee.
She left.
Oh my God, okay. So in collaboration with a person at NJIT, New Jersey Institute of Technology, Yoonjung Lee, she does cardiomyocyte research, and she takes embryonic stem cells, differentiates them towards cardiomyocytes. And what we saw was when we load cells in 3D, they start spontaneously differentiating. And if you add factors, they start differentiating. And you've got tissue, 3-dimensional tissue. Can't say it out loud because they haven't published it or really talked about it, but it beats, right? So it's very exciting work. Anyway, we injected some of these scaffolds into a subcutaneous model. Depending on the concentration of scaffolds, the pH and what have you, they either rapidly degrade or they stay as a bolus. Essentially, the implants we've done so far, they rapidly degrade, and what we see is that there's no overt inflammation, granulocyte, or what have you, infiltration into the vicinity of where we implanted these gels. So the last thing, that's pretty much what we've done so far. What we want to do, we just got our dog iCook approved 2 days ago. I was very happy about that. And what we want to do now is to essentially drill through the enamel, extirpate some of that pulp, remove it, inject it with our hydrogels, and then come back after a week, 2 weeks, a month, 3 months, and see whether we've actually reformed vital pulp. And the question really is, do you need, for the dentists in the room, I apologize, do you actually need to form vital pulp, living pulp tissue, or something that's responsive, right? Something that has the blood supply, so to fight infection, that has dentinogenesis, which may not be exactly pulp, right? So pulp-like tissue regeneration. So that's a little bit of the feedback we got from the first R21 that was rejected. So that's pretty much what I'm going to end with. I'd like to thank, again, my postdoc, Peter, who has had to deal with a lot of my students, specifically William Gao, Saloni Patel, both future dentists, who have worked primarily on this project. We've got a variety of other projects going on, different kinds of mimics, tack them on, treat different kinds of diseases. anti-angiogenic diabetic retinopathy. You saw all those macrophages infiltrate. We've shown that they phagocytose them in the intracellular vacuoles, degrade them, and hopefully they'll load them on MHC for presentation of vaccines. So we're tacking on a domain that I'm not going to tell you exactly what it is, for vaccine development for HIV. We're working with Royal School of Public Health on that, and we're working on a variety of different applications as well. I'm just going to stop there. If there's anything that interests you, please let me know. And yeah, that's it. That's all I got.